In this video, we're going to look at another example of centroids and moments. The question here is to find the centroid of the region above the semicircle x squared plus y squared equals 1 and below the ellipse 4x squared plus y squared equals 4. Y larger equal to 0 and density rho is equal to 2. The first step is to sketch a diagram. So we're basically looking for the centroid of the region between the ellipse and the semicircle. So this is a region here. We would like to find the centroid of this region. So we draw an arbitrary slice and we're going to find the mass of this region, the moment with respect to the y-axis, the moment with respect to the x-axis, and use the formulas to find x bar and y bar, the centroid of this region. So let's solve for y in terms of x. We're going to need it later. So solving for y in terms of x for the ellipse, we get y is equal to root of 4 minus 4x squared. We take the positive root because we're looking for the top half of the ellipse. So this is the half ellipse. And for the circle, solving for y in terms of x, we get y is equal to root of 1 minus x squared. And this is a semicircle. Semicircle. All right. So now let's apply the centroid formulas to find the mass moment with respect to the y-axis and moment with respect to the x-axis. So the mass is density times the integral a to b, top function minus bottom function times dx. All right, mass is equal to, the density is equal to 2, integral a to b from -1 to 1. The top function is, of course, the ellipse. Looking at the graph, the top function is ellipse, and we have solved for y in terms of x. So we're going to get root of 4 minus 4x squared, that's the equation of the ellipse, minus the equation of the top half of the ellipse, minus root of 1 minus x squared, which is the equation of the top half of this circle, the semicircle. All right, so mass is equal to 2 times integral from -1 to 1, root of 4 minus, now let's write this in a different way. Let's write it as 2x, the whole thing squared, so we can apply the substitution technique. And we split up these integrals, minus 2 times integral from -1 to 1, root of 1 minus x squared, dx. Now for the first integral, let's apply U substitution. Let me write this down, U substitution. So U is equal to 2x. Differentiate both sides, we get du is equal to 2 dx. Now let's plug the lower limit in, x equals -1. Plug it into u, u is equal to 2 times -1 is minus 2. And put the upper limit in, x equals 1. Plug it into u, u is equal to 2x, so 2 times 1 is equal to 2. So now we can change the limit. So mass is equal to 2 times integral from -2 to 2. So important, these are x limits, x equals -1 and x equals 1. Now we have u limits, u is equal to -2, u is equal to 2. And the reason for that is because we did a change of variables. The new variable is u is equal to 2x, so we have to change the limits. And we get root of 4 minus u squared times dx. If we solve for dx, dx is equal to 1/2 du. So let's put that in, 1/2 du. Now looking at the second integral, let's just copy that down. Integral from -1 to 1, root of 1 minus x squared, dx. This 2 cancels with this 2, and we're going to solve this integral using geometry. So mass is equal to integral from -2 to 2, root of 4 minus u squared, du, minus 2 times integral from -1 to 1, root of 1 minus x squared, dx. Now we can solve these integrals using trigonometric substitution. For the first integral, we would do u is equal to 2 sine theta, I guess. And for the second integral, x is equal to sine theta. But that's a lot of work. So let's apply a shortcut. Let's apply geometry to solve for the 2 integrals. The first integrand, root of 4 minus u squared, represents a semicircle of radius 2. So the definite integral represents the area of a semicircle of radius 2. The definite integral represents the area of a semicircle of radius 2. So the mass is equal to pi times 2 squared, radius squared, divided by 2, minus 2 times, and the second integral represents the area of a semicircle of radius 1. So that's going to be pi times radius squared, divided by 2. So we get 4 over 2, that's 2, we get 2 pi, and 2 cancels out, 2 pi minus pi is equal to pi. Now let's look at the moment with respect to the y-axis. The moment with respect to the y-axis is equal to rho times integral from -1 to 1, x times f of x minus g of x, integrate with respect to x. This x represents the distance to the y-axis because we're finding the moment with respect to the y-axis. And this part, f of x minus g of x times dx, is the area of the vertical slice that we've drawn. So that's the formula, and we're going to plug these in. Moment with respect to the y-axis is equal to the density is 2, integral from -1 to 1, x times f of x, which is root of 4 minus 4x squared, minus g of x, which is root of 1 minus x squared. Integrate with respect to x. Now, this integral, this whole integral is equal to 0. The moment with respect to the y-axis is equal to 0. The question is, why? Whenever a moment is 0, whether it's the moment with respect to the x-axis or with the y-axis, it has to do with symmetry. So let's explore that. So the moment with respect to the y-axis is equal to 0. The reason is because the region is symmetric about the y-axis. If we look at the graph, let's look at the graph on page 1, you can see this region is symmetric about the y-axis. This part here is exactly the same as this part here. So the moment with respect to the y-axis will be 0. So the moment with respect to the y-axis is 0. X bar is equal to the x-coordinate of center of mass is moment with respect to the y-axis divided by the mass. So that's equal to 0. So it remains to find the moment with respect to the x-axis. Let's write down symmetry here, just so that it's on the paper, I should say on the computer. All right. The moment with respect to the x-axis is equal to rho times integral a to b 1/2 times f of x all squared minus the bottom function g of x all squared, integrate with respect to x. Now, the top function is the ellipse, and if we solve for f of x squared, well, f of x is just y. So f of x squared is equal to y squared, and solving for y squared in terms of x, we get y squared is equal to 4 minus 4x squared, and this is the equation of the ellipse, of course. And g of x squared, the bottom function squared, this is equal to y squared, and isolating for y squared for the semicircle, we get y squared is 1 minus x squared. This is for the semicircle. All right, so the moment with respect to the x-axis is equal to density, which is 2, integral from -1 to 1, 1/2, times y squared for the ellipse, which is 4 minus 4x squared, minus y squared for the semicircle, which is 1 minus x squared, integrate with respect to x. This will be an easy integral to do. 2 cancels with the 2, so the moment with respect to the x-axis is equal to integral from -1 to 1, 4 minus 1, that's 3, and we get minus 4x squared, minus 4x squared plus x squared, we get minus 3x squared dx. All right, so we have moment with respect to the x-axis is equal to integral from -1 to 1, 3 minus 3x squared dx. So the moment with respect to the x-axis is equal to, integrate 3, reverse the power rule, we get 3x. Integrate 3x squared, we get 3x cubed, divide by 3. Evaluate it from -1 to 1. 3 cancels. So now let's put the upper limit in and lower limit, applying fundamental theorem of calculus. We get 3 minus 1 minus, put the lower limit in, we get minus 3. And minus 1 cubed is -1 plus 1. So the moment with respect to the x-axis is equal to 3 minus 1 is equal to 2, minus 1 minus 3 is -2. 2 plus 2 gives us 4. All right, let's review what we have found. The mass of the region is pi. The moment with respect to the x-axis is equal to 4. The moment with respect to the y-axis is 0 due to symmetry because the region was symmetric about the y-axis. X bar, the x-coordinate of center of mass, is moment with respect to the y-axis divided by the mass. So we get 0 because moment with respect to y-axis is 0. 0 divided by the mass, which is pi. 0 divided by pi is just 0. So x bar is 0. Y bar is equal to moment with respect to the x-axis divided by the mass. The moment with respect to the x-axis is 4. The mass is pi, so we get 4 over pi. So x bar equals 0. Y bar is equal to 4 over pi. These are the coordinates of the center of mass. This is the centroid of the region. And let's show that on a diagram on the first page. So let's go back to the first page, page 1. All right, so you can see that we have x bar equals 0 and y bar is 4 over pi. 4 over pi is just a little bit above 1. So basically, it's somewhere in here. Somewhere here is where the centroid of this region is. All right, thanks.